Hi, this is a quick session on what do we mean by homoskedasticity. Now, in this session, I'm going to give you an introduction to what do we mean by homoskedasticity and why it's an important concept when we talk about linear regression. So, homoskedasticity, now, even though it sounds like a complex term, the actual concept itself is quite simple. The first thing to know is that homoskedasticity has to do with the error term in a linear regression model. So here you can see a simple linear regression model with just one regressor, but the same concept applies for multiple regression models as well. So here I'm showing you an example where we are establishing the linear relationship between the salaries of individuals and their savings in a particular city. So if you imagine, let's assume that there are about 10 million working individuals in a particular city. We are not able to get the data from all 10 million individuals. But what we will normally do is we would take a random sample, let's say 500 individuals or 1000 individuals, and get their salary and their savings information. And then based on that, we would establish the linear relationship model. So here, let's assume that this line here is the population regression line. Now, remember that in reality, you will not know the population regression line, because in reality, for you to know the population regression line, you will have to have all the data from the population. In our example, you need to have all the information from 10 million individuals who are working in a particular city. Of course, that's not possible, practical. It's not practical. So because of that, you will not have the population regression line. Now, let's assume that if we have the population regression line, so here, what I'm showing you here is that if my x equals 30, now let's assume these are in thousands. So if my x is my salary, if my salary is $30,000, so let's assume this is $30,000 here, some of the individual's savings would be less than what the population regression line says. So it could be somewhere here. And if you take another sample, random samples, you could have another individual who has a saving higher than what the population regression line says. Basically, what we are saying is that every random sample you take, the savings can move somewhere in this line. And the average of those is the population regression line. So this is called the spread of the error term. Remember, if you look at this formula here, the error term is simply savings, which is this is for the population regression line. So savings is the y. Savings minus what the linear regression model says. So based on your sample, savings could be here, the individual savings could be here, here, and for some it will be here. But what we are saying is most of the individuals will have a savings closer to the population regression line. You can see here that seems like almost like a normal distribution, which means the probability of individuals having savings close to the population regression line is high. As you spread away, as you go away from the population regression line, there are individuals who have savings away from the population regression line, but the probability is small. You can see this area is small. So basically what we are saying is, and the error term is basically the distance from the population regression line. So what we are saying is the error term has a spread. You can see it has a spread, which means it has a variance as well. Now, when the error terms are homoskedastic, what it says is that the variance doesn't change when the x value changes. In other words, when the regressor's value changes, the variance of the error term doesn't change. So in this example, if the salaries are $30,000, or even if it's $80,000, or even if it's $100,000, you can see the spread of the error term is the same. So that's what we are saying here. These are some technical terms. The variance of the conditional distribution of u. Now conditional distribution means, here we are talking about conditional distribution in relation to x. In this case it's salary. So conditional distribution means you know the value of x. So what we are saying is the variance of the conditional distribution of u given x, in other words for a specific value of x, does not depend on x. You can see the variance of u, is the same whether x is small, in this case $30,000, or if it's $100,000 or even much more. Now in that case the error term is called homoskedastic. So this is what here also I'm just showing you here. You can see, let's assume that these are actual observations from particular sample, and this is the actual population regression line. You can see the spread is the same. The spread is the same irrespective of which value of x it takes. So in that case we call the errors are homoskedastic. Now one thing to remember, in reality for most economical examples the errors are not homoskedastic, they are heteroskedastic. In other words, as the x value increases, the error term, the variance of the error term will increase. You can see here the spread is not the same. So for most economical examples that you will come across, the errors are heteroskedastic, but homoskedasticity is an important concept to understand, and I will show you why. Now the other thing to remember, if we take the 4 least square assumptions, they do not talk about the variance of the error term. In other words, if you look at the first least square assumption, it says that the conditional mean of the error term for a given value of x is 0. In other words, it tells us the average value of your error term for a given value of x is 0. That's one of the first least square assumption. In other words, it does not talk about the variance of u. So what that means is the OLS estimator, so these are the slope and the coefficients of our model, the OLS estimator, it remains unbiased, consistent and asymptotically normal even if the errors are homoskedastic or heteroskedastic. So that's important to understand. Whether the errors are homoskedastic or heteroskedastic, it does not violate any of these least square assumptions. But the special case is that if the errors are homoskedastic, in addition to the least square assumptions, we can say that the OLS estimator is efficient. Now we'll discuss these things in a separate video. So the special case about homoskedastic is that if the errors are homoskedastic, under the Gauss-Markov theorem, we can say that the OLS estimator is blue. So here I'm saying the OLS estimators are blue. In other words, in addition to meeting the least square assumptions, the OLS estimator is efficient. So what does efficient means is that the OLS estimator has the lowest variance, the error terms has the lowest variance out of all the other estimators. So basically, simply in practical terms, what that tells us is that if you have a couple of regression models, when the errors are homoskedastic, and if you choose that particular regression model, the OLS estimators that you will use for that regression model, the error terms of that regression model will have the lowest variance. So that when the error terms has the lowest variance, we call the OLS estimators are efficient out of all the other estimators. So remember, homoskedastic is a special case where the error terms, the variance of the error terms are constant irrespective of the x values. But in reality, most error terms are not homoskedastic, they are heteroskedastic. So that's something to remember. And in the next session, I will talk about heteroskedastic as well. So if you enjoyed the video, like them and subscribe to our channel, and also if you have any questions, just put them in the comment section and I can try and answer them. Thank you.